Hi guys, this is Miss Scott here. So in the last lesson, we talked about some properties that parallelograms have. What we're going to do today is see if we can prove some things are true about a quadrilateral, then we can show that it is a parallelogram. So we're going to be working backwards today. The four theorems that we have in this lesson are actually the converse of those four theorems that we learned in lesson 8.2. Our first theorem tells us that if both pairs of opposite sides in a quadrilateral are congruent, then the quadrilateral is a parallelogram. So if you can prove that this side and this side are the same length, and then these two sides are the same length, then it would be true that that quadrilateral is in fact a parallelogram. All right, the second theorem that we've got tells us that if both pairs of opposite angles of a quadrilateral are congruent, then you can also say that shape is a parallelogram. So this is the converse of theorem 8.4 from yesterday's lesson. So if we can prove that these two acute angles are the same, and then these two obtuse angles are the same measure, then you can say that that is a parallelogram. Our third theorem, theorem 8.9, says that if one pair of opposite sides are congruent and parallel, then that quadrilateral is again a parallelogram. So we're filling in parallelogram for almost all of these today. Okay, so that tells us that if we can show this side and this side are the same length, and this side and this side are parallel, then that has to be a parallelogram. So here, this is the only one that you're dealing with just one pair of sides. The other two, theorem 8.7 and 8.8, you need to have both pairs. Theorem 8.10, so there is actually a typo here, so if you guys could cross this out. This should say theorem 8.10, so I'm going to go ahead and erase this and rewrite 10 right there. Theorem 8.10 is dealing with the diagonals of a quadrilateral. So if it turns out that this diagonal and this diagonal bisect each other, then that quadrilateral again is a parallelogram. So this is the converse of the last theorem in section 8.2. So if they bisect each other, we have a parallelogram. So that would mean that this and this need to be the same length, and then these two pieces need to be the same length. All right, so now we're going to look at using these four theorems to show whether or not we think a quadrilateral really is a parallelogram. All right, so in number 1 through 4, we're going to pick which of those four theorems will show that these are parallelograms. So our first shape, well, I know this has four sides. So in a previous lesson, lesson 8.1, we learned that if it's got four sides, it's a quadrilateral, these four angles have to add up to 360 degrees. So if I can show that x is 75 degrees, I can use theorem 8.8 to show that this is a parallelogram. So I'm going to say x plus 105 plus 105 plus 75, that has to be 360 degrees because this is a quadrilateral. So if I combine these like terms, 105, 105, and 75 add up to 285. So now to get x by itself, if I subtract 285 from both sides, these will cancel, and we end up with x equals 360 minus 285 is 75. So now if we look here, I've got this angle and this angle, those acute angles are congruent, and these obtuse angles are congruent. So since that's true, if we remember from up above, theorem 8.8 is the reason that I can say this really is a parallelogram, because I showed that the opposite angles are congruent to each other. All right, in our next example, we got this side, 73, is congruent to this 73. 98 is the same length as 98, so since opposite sides, both pairs, are congruent, we can say that this is a parallelogram by that very first theorem that we talked about. So this is just using theorem 8.7. So that tells us this is a parallelogram. All right, let's take a look at example 3. Here I've got 10 and 10 for these two sides, so these are in fact congruent. And these arrows here tell me that they're also parallel. So in that case, one pair of opposite sides is congruent and parallel. So if you look up above, theorem 8.9 tells me this is a parallelogram. All right, and our fourth example here. I've got two diagonals here. And if we look at the numbers, this and this are both 3.6, so they are congruent. And these are both 5. So if the diagonals cut each other in half or bisect each other, theorem 8.10 tells us that this is a parallelogram. All right, so there's our first 4 examples. In the next 2, we're actually going to be solving. So if we see here, we have, for what value of x is the quadrilateral a parallelogram? Well, I see that this diagonal is bisected by the other. I need these two to be congruent in order for this to be a parallelogram. So in other words, I need 2x minus 1 to equal x plus 5. So we're just going to go ahead and solve this for x. First thing we can do is add 1 to both sides. Then these will cancel. And we end up with 2x equals x plus 5 plus 1 is 6. So now I'm going to get rid of this x on the right-hand side by subtracting it. So 2x minus 1x leaves me with x is equal to 6. All right, so if x is 6, that's going to make this side here, 2 times 6 would be 12. 12 minus 1 is 11, so I get 11 here. And if I plug it into this x, well, 6 plus 5 is also 11, so that would make each of those diagonals, or each of those pieces, 11. So the diagonals would bisect each other. Okay, in our next example, we have, again, a quadrilateral, and we're trying to prove that it's a parallelogram. Well, I have one pair of opposite angles that are congruent. I need to show that both pairs are. So I'm going to take 360 degrees and subtract those two 101 angles. And if I do that, that's 360 minus 202, which is 158. So in order for this to be a parallelogram, I know this x has to equal this as well. So I've got 158 degrees left. That has to be cut in half, and each of those angles, including x, would have to be 79 degrees in order for this to be really a parallelogram. Okay, we're going to look into what if we have a quadrilateral graphed. How can we show that that is a parallelogram? Well, there's actually 3 ways. You can use the distance formula to calculate the distance of both pairs of opposite sides. And if those are congruent, you can then say from theorem 8.7 that really is a parallelogram. So this is actually just using theorem 8.7. You can show that both pairs of opposite sides are parallel. So you can calculate the slope of each side and then see if the opposite ones are the same. That's actually just using the definition of a parallelogram. So looking back to lesson 8.2 again. Or you could use theorem 8.9. And remember, that theorem is just showing one pair of opposite sides are congruent and parallel. So for this one, you would need to use both the distance and the slope formulas. So I'm actually going to do the third way in our notes just to show you guys two different formulas, so how these formulas work. So let's take a look. All right, so first step is just to draw A, B, C, D. So we're going to plot these 4 points. A is left 3, down 4, -3, -4. B is at -1, 2. C is at 7, 0, so we're just going to go right 7. And D is at 5, -6. So here is our quadrilateral, and we're trying to prove whether or not this really is a parallelogram. So I'm just going to focus here on this side AB and this side CD. I'm going to try to show that they're the same length and they're parallel, because then I've used theorem 8.9 to show that this really is a parallelogram. All right, so first thing I'm going to do is figure out how long AB is. So to figure that out, we're going to use the distance formula. So the distance formula is actually just based on the Pythagorean theorem. If I would put this triangle in here, this right triangle, I'm just really calculating this right here, which is the hypotenuse. So I notice this length from this vertical length is 6, and this horizontal length is 2. So AB is actually just the square root of that one leg squared, so 6 squared, plus 2 squared. All right, so if you would calculate that, 6 squared is 36, 2 squared is 4, so 36 plus 4 is 40. So AB is the square root of 40 units long. I'm just going to leave it like that. All right, now we're going to do the same thing with CD. So if we look here, if I put that right triangle from C to D, I notice here that from C to D is 1, 2, 3, 4, 5, 6 vertical units, 2 horizontal units. So I actually notice that this is the same thing. We got 6 squared plus 2 squared. If I take the square root of that, I get the same thing. So the opposite sides have the same length. All right, now I've got to look at the slope. So M stands for slope, so the slope of line AB. If you remember, slope you can also calculate by just taking the rise over the run. So for AB, well, my rise is 6, I go up 6, and I go over 2. So 6 over 2 would give me a slope of 3. The slope of the second line, line CD, again the rise, so to get from D to C in this case, we have to go up 6 and over 2. So our rise is 6, our run is 2. So again, we end up with 3. So since these are the same, then we can say ABCD really is a parallelogram, because we showed that this side, side AB, is the same length as side CD, and we also showed that these had the same slope, so they must be parallel. So therefore, ABCD is a parallelogram. All right, so use those 4 theorems to show whether or not a parallelogram is really what you're looking at.